hand, although strictly speaking, I thought I brought 3. Although strictly speaking, the Goldstone or Nambu-Goldstone case is not what the standard model is all about. It helps to grasp the delicacy of spontaneous symmetry in the case of gauge invariance. Okay, you will see how it helps. Some of the main features that we will encounter here, it should be understood. But the crux was the discrete case, right? We started with the discrete case, a simple Z2 symmetry. And maybe I could even wish the blackboard was bigger because then we'll keep it here. Well, let's try. In this case, I had a real scalar field with the, let me write symbolically now. The simplest possible Lagrangian we can write, and we took this to be lambda over 4 phi square minus v square square. And we found out the crucial thing is that there was no tunneling. Remember what I said? The way they tunnels is sort of the bubble creation of a, to understand tunneling, well, let's draw the potential. The advantage of a discrete case, that it's all very clear. And the way I draw it, it should be like this, the way I wrote it. And then we said that we have to live here, or that we can live here. We'd like to live there. It's not a question that we have to live there. We'd like to, even in quantum mechanics, maybe you and I would like to live there, but we can't. Right? If you are quantum mechanical, no, you and I can, because we tunnel. Okay. And the thing to understand it was actually to study the case when the degeneracy is broken, because then you expect to tunnel, right? And you find yourself, you and I, we find ourselves here, and we ask the question, okay, this is the study of Okun, Zeldovic, and Kobzarev, and then elaborated by Coleman in the 70s. We said what will matter here, a bubble will be formed. So you have a vacuum, let's call it, this is a plus or minus. The minus is not a vacuum, right? The ground state is actually plus. Well, it's a locally ground state, so we could even talk of local and global ground states. We could still use this language, okay? And so you form the bubble, and the bubble has a wall. And it has a wall because it's going to cost you energy to change the derivative of the field in that direction, of course. So we said the fight is, so this is the true vacuum, we call plus, outside is the false vacuum. We found ourselves in this bubble. And what happens? Energetically, you would say, well, it's favorable. So you could write even the factors 4 pi r cubed, and we would call this delta V, say, the split between the two vacua. This, of course, wants the bubble to grow. Immediately, exponentially, it wants to grow. The trouble is that the energy that I just mentioned is paid price in the surface, right? The volume term clearly wants you to that. So if there is some tension in the wall, and there will be, because once again it will cost you energy, right? But you think of the derivative in that direction, okay, you have to do this cross. And so there will be a tension times 4 pi r squared. This wants the bubble to shrink. And the reason that it costs you energy, think of among other terms here, there is a term 1/2 d phi over dr, everything squared, that you have to integrate over the thickness. Okay, and what will be the delta phi? Delta phi has to change its value from, imagine, it has to do a quantum jump. It has to jump from here to here, right? So delta phi here, this would be proportional to 2v over the thickness, which I can call delta, over 2 delta. Right? This is roughly, when delta is small. So this calculation is done by Coleman, is what is called a thin wall approximation. Otherwise, you can't do an analytical simple. You can't find a simple expression. You have to do it numerical. It can be done in this case. And then you would integrate over the wall thickness. So there will be 2 times 2 delta. So anyway, it's of the order of E squared over delta. But can you guess what the thickness of the wall would be? It's the only scale in the theory is V. Except for this tiny breaking of the symmetry, there is no other scale. So by the way, we could even have a homework problem on that. This is something that we call a domain wall. In the case of spontaneous breaking of discrete symmetry, we find out that there are classical solutions, they're called topological solutions, in which actually you form a domain wall between the 2 possible vacua, just like in the ferromagnet. Because you cannot go, it costs you energy to go from one to another. There is no continuous symmetry that allows you to go smoothly. You have to jump from one side to another. And it's sort of nice because in this particularly simple example, we can actually find an analytical formula. We can compute everything, the solution, the thickness. But you can guess at the end. And this is in particular of the symmetry breaking of type of Nambu-Goldstone-Higgs. The only scale is this vacuum expectation value. So everything that carries dimension will be determined by that scale. So if you ask what will be the mass of the fermion that you get in the theory, well, it's going to be proportional to that vacuum expectation value. And the mass of the gauge boson, you see. And the mass of the Higgs boson, because that's the only scale. Also the thickness of the wall, there is no other scale. So it turns out that delta is 1 over V, because that's what it has to be. It's not even so important, okay, I'm just trying to help you to see that T should be of the order of EQ. There are only 2 parameters in this model. One is V, and the other is this tiny breaking. We can actually say that delta V, say epsilon times V to the 4th, which is a dimension. And we could take, this is dimensionless now, to characterize it. Whatever is this differential here, I can always write it like this, okay? This is just definition of epsilon, you agree? But all what is important to take into account that there is a struggle here. So once the tunneling, once the radius gets bigger than the critical one, the tunneling starts, the bubble will grow. Otherwise it will shrink. If R is small, bubble shrinks. So. And what Coleman finds, that gamma, the tunneling is proportional, there is a prefactor, but it's proportional to 1 e to the minus epsilon to some power. It's very, very suppressed, exponential. Okay, in other words, this goes to 0 when epsilon goes to 0. This is why there is symmetry breaking. Finite degrees of freedom in quantum mechanics. Fortunately or unfortunately, depends how you look at that, okay, you would Since I wrote this, maybe let's just keep it that we said the field, really, the physical field should be V plus H. If you and I decide to live here. By the way, it tells you that you and I, as you get older, you learn that instabilities of life are more than you thought when you were a kid, right? The lesson tells you, well, nothing seems to be stable, right? Earth will die, sun will die, the universe may die. But what you learn that even the vacuum in which you and I live, we may not be stable. Maybe we live here, we don't really know. As long as the tunneling is slow, you and I shouldn't worry too much. Although the situation is apocalyptic. right? If I find out, I compute the tunneling and I find out it's much bigger than the age of the universe, who cares? Knowing the universe itself, as you know, it's getting colder, for example. It's not going to be good for life, so we are told. If we could reverse the Big Bang, right? Well, maybe then we could hope that we could create once again what this life was. But unfortunately, the one we live in would die, you know. It's apocalyptic one way or another. So among things that was learned, there was even there was a fear of false vacuum. There is a well-known paper, or papers actually, of Linde and Weinberg, separately written, putting the limit on the Higgs mass in the old days. I won't talk about it because it's irrelevant. Asking that we live in the absolute minimum. Now we know it's wrong, after it was understood by Coleman. What is very interesting in the case of tunneling, that gravity may playing an interesting role. You would never expect that. You would think, oh, I forget about gravity. That was the argument that I keep repeating from the beginning, right? But I can come back to it after you go through your gravity course. You didn't do Schwarzschild yet. Some of you may know, but I want to make sure that all of you know it. And then I'll come back to this issue. And for sure, I'll come back one way or another to the issue of domain wall. Now, it may be a homework or a discussion or whatever. Okay, this is something worth knowing. At this point, I stop here.
But if you had a continuous symmetry, would you still have domain walls?
No, you can't have domain walls. What happens, you can imagine that they become unstable because there is an extra direction in which you can sort of, you can circumvent this problem, okay? So there are two ways of thinking. One is understanding topological there will be. The other is to show how it will become unstable, right? You can compute small perturbation. You will see that it will immediately destabilize itself. So it's very interesting. When we break a discrete symmetry, we get a domain wall. Now you can imagine why we get a domain wall. Think about it. The crucial thing here, well, let's keep this. Let's try to. It's not going to be easy, but let's try. When we note this, I'm going to erase this because this is not what we are going to be talking about. I don't have enough space. What I'm going to keep, and anyway, this is a sophisticated subject. I don't expect that you've learned it here. All I wanted you to sort of get a glimpse of how he treated it. We go back to the generate case. So we have phi h, so we should write the potential among other things. Potential will be 1/2 mh square h square plus lambda v h cube. There'll be obviously an h cube term because of v plus h, and there will be a quartic term. mh square is 2 lambda v squared. This is the first example of what I was saying of mass scale being determined by the v parameter, the only physical scale in the theory. What was important for us was the vacuum manifold, which is set of all points that give you V minimum, which is set of all points phi 0 so that V is 0, that's the minimum, which is set of all points phi 0 square equal V square, which is plus or minus V. Vacuum monopole, the topology of vacuum manifold in this fancy language is just 2 points. So you may not be surprised, think of the z direction, okay, in which, imagine this is a point plus v and the point minus v in my field, that you find this domain wall solution. It's like this table here. Just imagine it very, very large, infinitely large. Then you have the symmetry, this discrete symmetry. Obviously, right? We often like to, no, let me not say anything more. Later. Except that we shouldn't be surprised if we find solution whose topology reflects the topology of the vacuum. Okay. Remember this in this case. The solution is a domain wall which is like an infinitely big table. The Nambu-Goldstone case, which is much more interesting, was a complex field that allowed me to have a symmetry. Well, maybe I can even write Q just to be a global symmetry. Alpha is a constant today. And Q is 1, we took. We said, well, Lagrangian will be, I wrote it actually as d mu phi square minus v of I, which had to be lambda, just because of the normalization, phi square minus v square over 2. Remember, I used the normalization, I normalized the field a little differently, because when I decompose it into the real and imaginary component, I put the square root of 2. I think it is obvious that it has to be absolute value square, right? Because of the symmetry. There is no other term. So it's basically the same potential. You see, everything is here, the essence of symmetry breaking.
You forgot this one.
Sorry?
You forgot this one.
Yeah.
Thank you. And the vacuum manifold, we set all points phi 0, so that V0, that's the minimum, and that is set of all points phi 0 square is V square over 2, and that we said is a circle. And then we said we can as well write this as V plus H plus IG. And we decided that G will not stand for boron, but rather, well, I don't know then whether it should stand for Goldstone, because Nambu actually noticed this, and Goldstone generalized. And we wrote this now in terms of the physical fields. Why? Because these are the fields that live around the vacuum, right? I can draw the same picture with a Mexican hat, because of the extra dimension. It's sort of something like this I have now. This is phi 1 and phi 2. And V, right? And its immediate calculation gave us mg equal to 0. We got mh squared equal to lambda v squared. Once again. And we got mg equal to 0. And it wasn't sort of obvious why we got mg equal to 0. You can think a little bit, it's not the field that accompanies the path, right? This is real and this is imaginary the way I wrote it. Okay. But the calculation gave us And there were terms similar here. There was a cubic term, there were quartic terms, both in H and G, and so on. Not very illuminating, okay. But the important thing was this interesting thing of mg equal to 0. This is often sort of for fun almost when we speak like that, okay? If I talk to my peers, I will often say that I'm here in the renormalizable gauge. There is no gauge freedom here, right? I have a global symmetry. This is a choice of this is a choice of variables. I think it's obvious that I don't have to dwell too much on that. How I choose my variables is up to me. Physics should not depend on the choice of variables. It's obvious. There was this article by Weinberg. Weinberg has a very dry sense of humor. You will never see him as a man of humor because he was always very serious. And then he's giving advice to young people. I remember one of the advices was rule number 3. When you choose your variables, make sure you choose the right ones. He says, why? Otherwise you may regret your choice. Now, why he said that? You will see that it's all going to be a choice of variables. And he goofed. He didn't choose the right variable. That Hopf came and chose the right variables. And I'm going to show you before even you go to the gauge case, how the choice of variables may help you sometimes to compute easier, but makes it harder to interpret. For example, you can compute here very easily. Everything is linear, right? There is nothing strange happening here. This is the most natural way to work, to compute. And I think even Hassan or someone suggested, why don't you just decompose it in a real imaginary? But I don't understand in this particular, a few things I don't understand. I don't understand why this guy is massless. I don't really understand. I did a calculation. I don't even understand very well the interaction of the Goldstone boson, okay? It looks complicated. It's something in the potential. But I could have chosen, so let me call this phi renormalizable for fun. Renormalizable means I can do a calculation. For us, you and me in this course, renormalizable is just going to mean you and I can compute, okay? This fancy language, it turned out. I can also choose phi unitary. Unitary is often a language that is used when you can get a physical picture. Okay, historically called unitary. I could have written it like this, I said. I think we stopped here. That's my right, you agree? But you notice that phi unitary square, absolute value, is 1/2 v plus h squared. And I understand immediately why G is a number Goldstone boson, why it has to be massless. It's not there. By the way, I performed a magical trick. You should be impressed. I got rid of the guy. It's really, took a handkerchief, turned it into a pigeon. I had a complex field with 2 degrees of freedom, and I made it real. It disappeared. And I understand why it has to be. Remember that there is a freedom here in rotating the phase, right? Which really means that G goes into G plus V alpha, sort of. So it's not surprising what I learned next. Where did G go? I can't lose G, right? I'm not that good. He went here. Because if I write d mu phi unitary, what will I have? I'll have 1 over square root of 2 d mu h plus I v plus h d mu g. You agree? So you see, G, of course, is there. I couldn't make it disappear. But I got rid of it, out of it, the potential, and I did something crazy, really. I'm not going to do calculations with that. It's very hard to do it because now I get a derivative interaction, okay? But still, it helps me to understand what is going on. I can write this 1 over square root of 2, d mu h. I don't need a bracket. D mu h. I can even take plus, well, no, let me write like this. No, there should be d mu g over v. Nobody corrected this time. There is I g over v. And I know dimension, it has to be there, right? It should be the same dimension. So I have I 1 plus h over v d mu g e to the I g over v. So the kinetic energy d mu phi, I keep calling it unitary square, would be 1/2, and I will have d mu h squared plus d mu g squared, the first piece. I get correct kinetic energies. Okay, that's not surprising, that's my normalization factor. Plus, however, there are extra terms here. For example, let me just write a leading term would be h over v d mu g squared. And there will be also a squared term. So notice what happened. The coupling necessarily is derivative. Well, it's derivative because it has to respect the symmetry. G is a phase. The only way to respect this transformation property, if I depend derivatively on G. I'm not surprised that I got this. So in this so-called unitary gauge, it's a lousy language, there is no gauge. In the unitary field that I've chosen, in this particular choice of my variables, I won't want to do calculations, okay? Maybe sometimes, I could even sometimes do a calculation depending what I want to do. Should I don't want to do loops with such a terrible derivative coupling. But what I understand immediately that, so what I've learned about Nambu-Goldstone boson is 1, their mass is 0. 2, their coupling is always derivative. I can always go to this basis, to this choice of variable. And that means it's suppressed by the vacuum expectation value. I will always get a coupling of this form with whatever it couples to. This is very useful to know. For example, it's proportional to the momentum, right? When I go to the momentum space, to the energy in question. And if for some reason I learn that this coupling should be small, I would translate it into saying that V has to be large. I know what I mean. V would have to be large compared to the physical scale that we are discussing in the question. And maybe we could actually say a few words. We are contemplating the existence, and we think this could be physically possible if I break spontaneously a global symmetry, like here. And remember what spontaneous symmetry breaking was. Q phi 0 was not 0, obviously. That's what we interpreted as spontaneous symmetry breaking, obviously. There is no ground state, which is really a vacuum. I keep calling it vacuum, but it's a lousy word. It carries this charge. That symmetry is broken. The grounded state itself is charged. This is equivalent to spontaneous symmetry break. contemplate such a particle, it's going to be massless, we said. If it's massless, it will mediate what kind of force? A long-range force, just like the photon and the graviton. So that sounds crazy that I can contemplate it. By the way, we know that gravity is well tested at microscopic distances, but also at the distances of you know where you do that type of experiments. At distances, these distances. Actually, they went even below a millimeter now. In recent years, there has been improvement on the lower end. So between a millimeter to a meter, gravity is well tested. And it's very little space for yet another force that we could call fifth force. That occasionally, you know, some anomaly, some experiment shows up. Some years ago, the group of Seattle had an anomaly. They were actually saying the fifth force. Adelberger et al., brilliant experimentalists, great people. Consistent, they decided to publish the paper. It rains a lot in Seattle. My daughter was studying there, she was complaining always of this terrible rain. And it rains so much that when they wanted to be sure that they are right about what they were saying, they took into account the change of the weight of the hill, because it gets very damp. There is a hill near physics department. And they were scared maybe that the gravity got changed by accumulation of rain. You can imagine what extraordinary work they had to do. And they were consistently getting statistically relevant deviation from the Einstein theory. The one thing they didn't check, I think it was the problem of Westinghouse, whoever they ordered them. Their readings were badly, someone did for them and they never checked them. The transformations of inches into centimeters instead of 2.54. I don't know. There was imagine the strategy. Okay, you can't really blame them. Okay, it's very hard, you know. And it wasn't that crazy. This is not like the Grand Sasso experiment that found neutrino faster than the light. At the end, it's, you know, it was just that they didn't, you know, close something well. I mean, that's really a shame. That should have never been published. So you can ask, how in the world can I contemplate the existence of a particle that will change gravity? So let me say a few words, because actually the Goldstone bosons, a number of Goldstone bosons can actually exist. There is a caveat here. And the caveat is the same reason why gravity matters. The reason that gravity matters, it couples to the sum of the particles in question, couples to the mass in the static case. Now notice an interesting case, that in the static case, this guy doesn't want to couple. Right? This will be a momentum in the process, so it will go to zero. So somehow it tells us that there is hope here. There's a little more to it. But in order that I talk about the impact of this force, I need to bring matter into the game. You agree? And matter, of course, is fermions, right? I will often use this language. In gauge series, we speak of matter. That's what we mean is fermions, okay? Not the gauge bosons. They are messengers of the forces of matter. You and I are made out of fermions. We are matter. They are matter. Okay. So see, it's not easy. Something I have to erase, but I think I'll have to erase it in the end, because if I keep this, I can't keep that. Too bad. So let's introduce the fermion, just a single fermion. I want to couple it to my number Goldstone bosons. I could write a fermion coupling to the scalars. I call Yukawa couplings. This is a traditional language, right? Historic language of the Yukawa force that was supposed to be, the strong force was imagined to be the exchange of a pion coupled to a nucleon. So you had a scalar in the Yukawa theory, pion. The only difference, pion is not elementary, right? So I could try Yukawa interaction, add to the Lagrangian. In other words, the Lagrangian would be delta L, would be with this sign normally we write. It's an interaction. And Yukawa interaction, you can say, okay, you know how to couple it, right? It has to be Lorentz invariant. And it has to have the proper dimension, dimension 4. So it seems that the only way to write it would be this. Correct? Well, almost. Why is this wrong, actually? Why can't I write that? My Lagrangian has to be invariant. I have a U1 symmetry I'm claiming, which I should have said. There is a U1 symmetry. U is e to the I alpha q. This is U1. And by definition, I'm talking about spontaneous breaking of symmetry. That means I need to have a symmetry. This is not symmetry because psi bar psi is invariant. This could never be symmetric. There is nothing you could do, no matter what phase you associate with psi. But I can do something a little different. I can write like this. And immediately becomes possible. And actually, this is the way I should write, because I should remember that the basic fields, the irreducible representation Lorentz group, you and I learned, are the two-component object, the left and right spinors. I should always go back and think of that. It's just by sheer accident Dirac was lucky. We know. Because he worried about the electron. In the case of electron, left and right have the same properties, okay? They have the same charge, obviously. But when I have some imaginary U1 symmetry, this is surely not the symmetry of QED, right? This is not even gauged, so it's a prototype. Then, of course, it means that now the quantum numbers of left and right would be different, right? If I want to have a symmetry, I have to write like this. And therefore, I have a choice. By the way, now I have a sort of a set of possibilities. All that is that I know left and right cannot transform the same way. Otherwise, the phase would cancel. So we can say when phi transforms like this, we can say that psi L goes into psi L, and psi R goes into e to the minus I alpha psi R. Now I have a U1 symmetry. So let's choose this one. That's a perfect possibility. So if I write like this, let me first write like this. This is the way that you and I would, or like this. So I'm going to first use this, what I call phi renormalizable. And I will get to 1, this will become y over square root of 2. And then I'll get, well, okay, why don't I write immediately phi bar, psi L bar psi R is, in my notation, psi 1 minus gamma 5 over 2. My right was 1 plus, 1 minus, sorry, and left was 1 plus, remember? And this is V plus H plus IG plus Hermitian conjugate. Explicitly written, what I get is y over square root of 2. Notice the first piece, V plus H, goes out. This is real. And I will get this plus Hermitian conjugate will give me psi bar psi. No, yes, well, I should have been explicit. I don't help you by writing like this. I should have written the Hermitian conjugate is psi bar 1 plus gamma 5 over 2 psi V plus H minus IG. So, if I want to be explicit, I better be explicit all the way. You agree? This is psi L by psi R. Hermitian conjugate is psi bar R psi L. My L is 1 plus gamma 5 over 2. So V plus H is going to couple to psi bar psi. You see it? Gamma 5 will cancel. That's not surprising, by the way. This is a scalar. This is a scalar. A scalar is going to couple to a scalar. Okay. Whereas notice this is a kind of pseudo-scalar. Okay. It has this particular I factor here. And that's going to couple with a minus sign. So I'm going to have minus. There will be a factor y, g, but I'll get psi bar gamma 5 psi. Do you see that? 1 cancels now with g because the sign is changed, but gamma 5 stays. So notice the first thing, the mass of my fermion is y over square root of 2 times v. As I was promising, all the masses, this is the beauty of spontaneous symmetry break. Now you see, this field phi is a special field. It's a also mass. I will later on bring in gauge fields. Then I'll call it Higgs, but it's basically all here. Whatever gets a mass must be proportional to V. So we say that the field itself is a source of mass. Why? Because the vacuum is full of this scale and the charge, okay? The field living is some kind of ether and pick up mass, energy from the ether. And you know immediately how this guy field, you know, that we said later on we'll find out, it's called the Higgs field. It should actually have been called Goldstone notice first, or Goldstone Higgs. Anyway, from here, in other words, this will become then, there will be m psi, psi bar psi, plus, now I notice that Yukawa is just m psi over v, h psi bar psi. Yukawa is m psi over v. So two things I learned about the Higgsiness of this field, this extraordinary thing. It's the source. Its source is the mass is sourced from there, and then it's coupled to the mass. You will find out. The Higgs field in the future, I started calling it Higgs, okay, because that's what it will be, has a particular property very similar to the graviton. Graviton couples to your mass. But graviton is, however, different. If you start moving, graviton will actually know about that. And if you move very fast, it will couple more. It will couple to your energy. The Higgs never. Higgs really doesn't know whether you're moving or not. For example, if you move forever like a photon, then Higgs won't couple to you. Higgs can couple to you only if you give it a mass. Once you give it a mass, it couples to that. You see, because they go together. The mass term and the Higgs field go together. V is like a mass. We know that on dimensional grounds. We'll repeat this ad infinitum. So if it escapes to you today, it's not that great. But what I learned, that this guy also couples in the same manner. What I got here, this goes into minus I, m psi over v, psi bar, gamma 5 psi.
G.
G. Thank you. So I'm very much interested in the G particle. So notice it does go as 1 over V, as I suspected. I said that the Goldstone boson will always couple as 1 over V. I know that, because I can go into this stupid, strange, unitary way of thinking, and it's true there, it has to be true everywhere, that feature. But it's very strange, because what I claim here, that is proportional to the momentum, here it's not. There is some contradiction, apparently. We'll try to understand it. But before we do, I want you to I want to see whether you remember non-relativistic quantum mechanics. Did you do in the relativistic course? Did you repeat the? Did you go to the non-relativistic limit? Yeah. Do you remember? How does the non-relativistic limit spinor looks like? In the relativistic limit, remember what we did, we had this left and right, we projected helicities there, right? So notation that I've introduced from the beginning, the choice of gamma matrices, is ideal when the particles move very fast. Separating into this left and right. It's very bad for slow moving electron. Slow moving electron, how would the spinor look like?
It's kind of 1 minus sigma dot p over m.
Well, there is always, when I go to quantum mechanics, then I can talk of 2-component spinors. The 4-component is a misleading thing, okay? That means that this guy that I call V here, I can call them U and V, because V must be small.
Yeah, small.
And why is it small? It's going to be
Proportional to p.
2? To what?
It's proportional to p over c times something like that.
Yes, it's proportional to momentum, but that's a vector. So it can be vector times what? Times sigma.
Sigma.
Yeah, okay, this is very important. Sigma dot p. So what I mean when I say that, I'm not a limit, that p is very small compared to m. So this basically goes to 0 and p goes to 0. I think I could leave this as a homework. Let me think whether I should. Because you see, notice gamma 5, actually, a few words here. I think I have to erase this. Notice to the lowest order, you notice that this is one and the same thing, right? If I expand, the first term would look like this. Only here there are some interactions, okay? For small values of the G field, I will get the same result. So for example, if I want to read of kinetic energy, it will be the same whether I read it here or here, okay? If you've done it here, you don't have to repeat it, obviously. The leading term when you're ignoring interactions. So, so you see, when you look at the term psi bar gamma 5 psi, this is psi dagger, gamma 0, gamma 5 psi. This is the off diagonal, no matter what you do. You may choose gamma 0 diagonal, gamma 5 off diagonal, vice versa. I chose gamma 0 diagonal, off diagonal. That's good in relativistic case. Non-relativistic, you choose gamma 0 diagonal, and then you get this projection. But doesn't matter. This is off diagonal. So you notice that you are going to get something like U dagger, sigma dot p over 2m. U1 there will be two states, U2 between. If I want some interaction between 1 and 2, or different momenta. Okay, it doesn't matter. I don't want to do this carefully, okay, because I'd like to give you some homework. I just want to give you a sense. Let me even, not say much. The thing that will come out is not only is proportional, at the end it is proportional to momentum. You see, because I claim that the Goldstone boson coupling will be proportional to momentum, and it will be. But it's also proportional to what? Sigma. What is sigma? Sigma sandwich between the states is spin. So you understand why Goldstone bosons are not dangerous for gravity. Take a star like the sun. The spin of the sun is basically order 1. It's a vectorial quantity. If you look at large nuclei, they have a lot of protons and neutrons. The spin is still order 1, which is obvious, right? Because it wants to point up and down and sideways. It's a vectorial quantity. So the reason that gravity is strong, that gravity matters, the reason that matter gravitate, is the large number of protons and neutrons that give this coherent effect, not the strength of the force. The force is negligible. And the Goldstone boson may have a much stronger interaction, but it will not be very competitive, obviously. Because the sun, as you knew, well, the Earth has about 10 to the 50 protons, but spin 1, or 5, or 10. So you understand, you gain a factor of 10 to the 50. But I leave for you to do the actual calculation and not just hear it from me, I think. Okay. It's reassuring that no matter how I look at it, you see, in non-relativistic limit, I got what I wanted, okay? I have another way that you can still ask me, well, what would happen in the unitary case? Notice what I can do to confirm what I said here. So if I go now to phi unitary, this was phi renormalizable. And then now I put phi unitary here. Notice what I can do here. And once again, phi unitary is 1 over square root of 2v plus h e to the ig over v. I can write psi r is psi r prime e to the minus ig over v. You agree? It's just a choice of variables. It's very convenient for me to do that, to illustrate the point that I want to do that. Again, it's just a choice of variables. Just like this being a choice of variables. I'm going to drop this prime. All I want to tell you, the way I got rid of the Nambu-Goldstone boson in the potential, I can get rid of it in the interaction also. Right? I can always choose the variable so that the guy doesn't exist there. The phase can be taken out. That doesn't mean that I got rid of G. This is very important. This is a physical field. I can't eliminate it. So then my Yukawa interaction would be equal to, there will be no G. I don't even have to write it. Yukawa would be Yukawa over square root of 2 psi bar psi r plus psi r bar psi l v plus h. I can always go back to the discrete case as if there is no G. Notice, I can do that. What will happen? It will be in the kinetic energy, right? Once I do this transformation, okay, actually that should be prime, strictly speaking. Okay, let's keep it for a second. So G is gone. But there is a kinetic energy which has a left-handed piece, but it also has the right-handed piece. Psi r bar, gamma mu d mu psi r, which is I psi r prime bar e to the I g over v, and then gamma mu, and then I have two pieces, d mu psi r prime plus minus I d mu g over v psi r prime e to the I g over v. Maybe e to the minus I, thank you. Better. So what I get is the kinetic energy that I had before, plus or minus. It seems to have a minus sign, no, plus sign. I minus I, d mu g over v. You see, I got it. I got it as a derivative coupling. And then it looks like psi r prime bar gamma mu d mu psi r prime. Well, it has to be. In this particular way I'm doing it, it has to be because it has to do with the transformation property of G. That's what I got here, anyway. But then you can ask me, well, how in the world is this equal to this? They look different. Okay, you have to be very careful when you work with Goldstone bosons. I've often seen wrong papers because in this basis you will surely get the right result. You've used maximally the freedom of getting rid of the phase. Okay. Can you see why these two are equivalent? While I am Can you tell me?
Is there an additional derivative?
Sorry?
That term.
There is a derivative. Oh, maybe I maybe I have to have magic of indices, okay. We could get rid of this prime, right? Why carry on prime? I mean, it's just a change of the field. So it seems that I have a very different interaction from there. But can you see why this will not be different? What do you do when you have derivatives? You can always differentiate by part, right? So this actually, if I differentiate by part, will be minus g over v d mu. I get rid of the total derivative. D mu psi bar gamma mu 1 minus gamma 5 over 2 psi. Right is 1 minus gamma 5 over 2. Now what I want to establish is when I go on shell that I get the same result. Okay. And for this I need to use Dirac equation, which was I gamma mu d mu psi is equal m psi. By the way, this from here you can show that minus I psi bar gamma mu d mu acting here is m psi bar. You must have seen this. All you have to use is the properties of gamma matrices. Gamma 0, gamma mu dagger, gamma 0 is gamma mu. So I have two pieces, one when I act here and one when I act here. So this is minus g over v. When I act here, what do I get? I could multiply this by I. If I multiply by I, I'll get an extra factor y. So I'll get I think, correct, and then I'll get m. Sometimes I call it m or m psi. Okay, m psi bar one minus gamma 5 over 2 psi. I acted here. But there is another term when I act here. The only thing I must be careful, I have to act here. So that's going to change, it anti-commutes with gamma 5. So this will be 1 plus gamma 5 over 2. And then d mu gamma mu from here, I should multiply this by minus I. Well, I don't know what I should do. Tell me, help me.
Yes, minus I effects.
This, I just wrote it as this, then they will have minus m. So there will be minus m,
Yeah.
I think.
Yeah.
And put this.
One with x and another with x.
Phi, oh, phi bar.
No, because they are matrices.
Maybe better like this. Did you follow, all of you? The factor is different because these two equations, that's just a difference of sign. There are two differences. The bar equation has minus I, this has plus I. And the other thing is that I had to go through gamma 5, so it became 1 plus gamma 5. But basically it's trivial. So notice that this cancels. And I get minus plus, I don't know, I, G over V, and psi bar gamma 5 psi. I get the same interaction I started with. It's kind of reassuring that and they have to be, you know, when I go on shell, when I go to the physical quantity. Of course, in this equation, I ignored the interactions that exist with G and H. They will bring in higher order terms. I just want to show that the leading term is the same. What have I learned? You know, what is the message? I kind of, you know, we may have got a little lost, right? The first thing was very easy to see. Number-Goldstone bosons are massless. That was very easy to see, particularly in this unitary representation. What is not easy to see is the form of the interaction, okay? So the unitary choice of a variable that I call this particular one helps me to see immediately that the Goldstone boson interaction is going to be suppressed with that scale. And then, of course, it's obvious what has to be. For example, in this case, m comes out. In a static case, m will come out. The momentum will be hidden here, we found out. Okay. So this is very important, that the scale of symmetry breaking sets the interaction of a Goldstone boson. This is very beautiful. There is a particularly popular Goldstone boson. Imagine number Goldstone boson called the axion has to do with something which is called strong CP violation and so on. The beauty of the axion is the beauty of its interaction is decided by the scale. It turns out axion is actually not a real Goldstone boson, it's a pseudo Goldstone boson. It gets a little mass. It doesn't matter, there is some explicit correction. Okay. But just as in the case of any number Goldstone boson, you can change your model. You can have many different variations of this. You will always get this result. You see, this is generic. Doesn't matter what you do. The number Goldstone boson will always couple like this. because you can put it there. So you would imagine, of course, that V has to be huge because of gravity. You don't want the fifth force, we don't see, but we found out that spin will enter and spin is small, so actually you don't get a useful limit on V from gravity. But there is something else, a beautiful interplay of cosmology and particle physics, or astrophysics and particle physics. We have a field today which is called astroparticle physics. It started in the 70s when people started to be more and more sure about the Big Bang. Obviously, if you have a Big Bang, right, that's the first thing the particle physics and cosmology married beautifully, right, because the universe was hot. And it was so bloody hot, there were only elementary particles, so you and I can do cosmology, even if you are not cosmologists. That part we can study. I mean, you and I mean particle physicists. Imagining you guys to be particle physicists, now you're not really in your poll, actually, the least of your interest was particle physics. I find this mind-boggling. I don't know how is it that LHC didn't arrive to you. That finally we have a machine, you know. Lecture put it beautifully in the 80s when there was a debate, should you build or not build a collider? And then some people say, yes, you should build it because we have some final theory and so on, stupid things. And Gleshev says, well, take a shoemaker. A shoemaker needs a hammer. And this is our hammer. You can say it's a microscope because we see with that, but it's so basic that it's like a hammer. So I can imagine that you guys don't care about particle physics 20 years ago, 30 years ago. It was all about cosmology and there was no machine, so people talked about whatever fables they had in their mind. But we can do really particle physics today. There is a beautiful machine out there. And people are contemplating a bigger one. We can go back to do what physics is all about. Using field theory to make beautiful, clear predictions. Compare them with the experiment, and you lose goosebumps if it find it strange that you guys don't appreciate that. You know, the fact that you can compute the trajectory of a planet around the sun and then go and see, yes, it agrees with the experiment. Anyway, sorry for this little propaganda. Just to tell you, I've never computed, you know, I'm not really a philologist. If you look at my papers, they actually, some of my papers have cross-sections. I never computed them. The last cross-section I computed in my life was during PhD days. I have younger collaborators who then compute these cross-sections. So it's not a philologist making a propaganda, it's just a physicist telling you that that's the only way we can do physics. Everything else is words. Forget it. You will be lost. If you forget it. As I like to cite Newton, actually a few days ago, I can make a little propaganda, I posted it. You guys look at the archive, or it's too above your head. Yeah. I've actually posted a little essay on archive about physics being natural philosophy. I probably won't be able to appreciate it. Anyway, enough propaganda, let's do physics. I should convince you by facts, not by words, right? It's usually where we fail when we try to convince each other. I admit.
Maybe we can do a visit to the LHC and then people will start empirical physics, no?
Well,
okay, listen.
I don't know. No, I'm good point, maybe. Let me see if you have questions here. My digressions are often a chance to give you to have a question, you know, to make it less heavy. It's not me losing a thread. It's done on purpose to sort of make sure I stop whenever we have to move from what we've done.
Is there any problem with the minus sign? Yeah.
Why did I get a minus sign, you were saying?
Yeah, and the other, we got a minus sign there.
I don't think I got the minus sign because this is minus. There is a minus sign here in the Lagrangian. Kinetic terms goes with a plus sign. Every interaction goes with a minus sign. So there was actually an extra minus sign in the Lagrangian.
Okay.
This is Yukawa interaction, but I'm glad you asked me. I was actually not, before you asked, I wasn't sure whether I should worry. I just realized. It's sort of funny, as I was walking here, I realized one forgets that. I did. I'm glad you asked. It's not that the sign would matter physically, you get the exchange of a Goldstone boson. It's still good to know that we get it right. Okay, it wouldn't screw up anything, it would be good. But, you know, the fun of doing calculations is getting the right sign, you know, not only the right factor. Like there was a mistake in my homework. I think it's you, Sergey, pointed out, I made it.
But then why is not here?
Sorry? Because this is coming from kinetic energy where the sign is.
Okay.
This is the sign that I got at the end of the calculation, and here actually I should remember that I did Lagrange and there will be an extra sign. So when we do the, fortunately, you know, sometimes we can make a sign mistake in the direction. This is different from the amplitude. But when you exchange these messengers, like a number Goldstone boson or the Higgs, the sign would cancel, fortunately. Factor Y it may not. So this is one of the things that we can permit ourselves sometimes, not to worry about the sign of an interaction when you're looking at the exchange of that. But it's important to be. Okay, let's then maybe stop here, summarize it, not leave it. So I have two different ways of this may be actually good to keep. I have two different ways of using a variable, and this one, what I've learned, and they have to be, doesn't matter what I do, the mass of G is 0, this is what I said, and the coupling of G is always of derivative type. It fortunately agrees with this one. So maybe to summarize it, the third thing is the basic interaction, the matter interaction is of the form IG psi bar gamma psi psi m over v. This is the way the number Goldstone boson couples to matter. Now you can see actually there is one, I started to talk about that, a beautiful interplay between astro and particle physics here, is that although this is not so important, psi bar gamma phi psi is proportional to spin times p over m. Okay? Because of the spin, or let's say the average value of spin, it won't matter for gravity, but will matter for, can you imagine what could go bad? You see, if these guys couples to matter, then we couple to an electron and a quark, that's matter. But the sun is full of electrons and quarks. So what would happen if you had number Goldstone boson? The sun would not just shine light, but it would also shine, in other words, it would lose some of its light by emitting number Goldstone bosons. And that's not good. We don't want the sun to cool off. Actually, we know that sun has not cooled off. Right, this weekend it's hot today, it doesn't seem convincing, but sun will shine apparently in a day or two again. And that actually tells you that the coupling has to be small. So just sun implies that V has to be bigger than 10 to the 9 GeV. And just the fact that it keeps shining. I won't do I won't bug you with the details, okay? We may do something for the homework, we'll see, or I'm not sure here, but forget the details. All I can tell you, I'm not going to put the numbers, that unless the scale is very large, you see everything is fixed here. I know how it couples. M over V, if I go to the small momentum, non-relativistic, I can figure out what happens. The people did these calculations immediately when the picture of Nambu-Goldstone, the axion, when it became very popular. And they found out that you couldn't have an axion in the standard model. You see, in the standard model, what is the value of this scale? Can you tell me? Without knowing anything about the Higgs mechanics and whatnot. What will V be in the standard model? Roughly? Well, remember I said it's the source of all the masses. What will be the rough value of V in the standard model?
100 G.
What's the scale? 100 GeV, that's the scale of the standard model. W is in masses. If I'm right, and somehow this is happening, then also W and Z mass will come out proportional to V because there is no other scale. What else can it be? And W and Z masses you knew are around 100 GeV. Therefore, the scale V is about 100 GeV. By the way, I can't associate the number. It depends how I normalize it. I could put the square root of 2 or I don't put the square root of 2. It's up to me a little bit. But roughly it's 100 GeV. Notice the huge limit. So if there are Nambu-Goldstone bosons, they associate with large scales. They bring in new physics far from us. And this is why, you know, it was 1977 when, for example, this particular Goldstone boson axion was suggested by Weinberg and Wilczek separately. And it's still searched for. You can imagine it's hard to find a particle which is coupled so weakly. By this being large, this becomes extremely small. Or better to say, they first compute that this coupling is very, this I called you Kawa, remember? Over square root of something. So you compute, you put the limit on your Kawa. So it's not of immediate interest, obviously, the physics of Nambu-Goldstone boson. Okay. What we are going to do, we could think a little bit, I'll decide by Wednesday. I could go immediately teach you the Higgs mechanism, we understood this. But we want to also do non-abelian examples, so I will either continue Nambu-Goldstone with non-abelian example, or I do the abelian example Higgs, and so on and so forth. What we have to do, you know, we are getting there. I'm slowly giving you a picture. All we have to do is understand the symmetry breaking in a little more complicated theory, not just U1, like SU2. So since I'm going to stop here, remember what I said, the vacuum manifold being of this form is a circle. So can you guess if there are such solutions that I call topological? In the case of a discrete symmetry, I found out that I could actually find explicitly a solution. I should have written it. In the discrete case, remember when there is M0 is plus V and minus V, there is actually something which is called domain wall, or sometimes a classical solution as a function of Z coordinates. So imagine an XY plane. Imagine this table being enlarged. And it looks like this: V tangent hyperbolic VZ. So what it does is, if you plot, notice what it does. It does something like this. This is what I call domain wall, connects the two different vectors. So in other words, there is something, and in cosmic energy, it goes through zero when there is a lot of potential energy, in other words, cosmic energy. So I just asked this, can you guess what will be the form of the solution for this, but if it exists? just by symmetry argument. You see, the thing is that this classical solution, the topologies are such that they match the symmetry of the vacuum manifold. So the thing separates these 2 points. Well, it's something which is a circle, and that there has to be a string. But forget it, it's not a place to learn. Just an en passant statement. Let me know if there are questions.
But it has to be what? String?
A string. The string would have this circular symmetry. So if you have a vacuum which has a spherical symmetry, you will get a solution which has a spherical symmetry. It will look like a little ball. It's not surprising that there is this matching, okay? There is no time to speak about that at the moment. It's a beautiful subject, by the way, and if any of you are interested, I can tell you what to read. But let's see if there's a question, urgent question. We get a minute or two, so. Okay.